really positive and impactful meeting for you all whilst you're here. And without further ado, I would really like to welcome Rob Jackson up to the stage. Rob, who many of you may know, has been working for many years in the field. He's a professor at Stanford and has been contributing most recently to really important efforts towards the global FluxNet methane data set, amongst many other things that Rob will tell us about. One of the most interesting recent events, perhaps, is the publishing of a book, which I hope we get to hear about. I don't know if there's a signing later. Um, Let me move this here, and I'll just unplug. Apologies.
Okay, thanks. We're all wondering what Trevor did. Soccer. No. Had a little trouble going full screen earlier, so we'll do it the old way. So that'll work. So first of all, Margaret, Trevor, and all of you, thank you for organizing this great annual meeting and for hosting us here to Berkeley. I'm Rob Jackson from down the bay at Stanford, and my outline for today is a little science, a little history, a lot of methane, and a lot of community engagement. That's really why I'm up here, is to try and build the FluxNet methane network with you and other people. So thanks for having me. I chair the Global Carbon Project, is one of my favorite things I do professionally. We're just about to launch our new global methane budget, which will be published next week. And there'll be some new aspects to the budget, particularly around wetlands and freshwater ecosystems. So keep an eye out for that. And I would acknowledge my GCP colleagues, Marielle Sonwa in particular, who leads the methane budget. Well, first of all, why methane at a meeting like this? Methane, I think, as most of you know, is a very potent greenhouse gas, say 25 to 80 or 90 times more potent than carbon dioxide, depending on the time frame that you look at. It has also risen much more than carbon dioxide has. We're now about 2.6 times above pre-industrial levels. And the last 5 years saw the fastest increase in methane of the instrument record for reasons that we're still trying to tease out as a community. So that's the why. It's also the strongest lever we have to slow global warming in the next decade or two because of its potency and its relatively short lifetime in the atmosphere of only about a decade. So that's my pitch for why methane. And I think, as most of you know, methane emissions are dominated by things that we do. And those things are primarily agricultural and fossil fuel. So you may not be able to read that in back. The orange bars are anthropogenic sources. That largest one, I guess I do have a pointer, 2 to the left. I know one of these buttons must, there we go. But you can't see that anyway. So the large orange button is agriculture, and that's about 200 teragrams a year. The fossil fuel sector is about 100. The large green arrow in the middle is the arrow of interest for us today. That's the wetland and freshwater emissions. That's the largest natural source. So we'll be focusing on that today and thinking about ways that the FluxNet community can contribute to understanding those emissions today and providing a baseline for change and assessing change in the future. That's really our goal. And then the sinks here are on the right. So we'll focus on wetlands, and the sort of the bottom-up inventory approach has wetlands in the upper left of this panel. Each of these dots is a site of emissions and an estimate of the intensity. The more red, the higher the emission rate, or higher the flux. You see other factors here: fossils, ag, and biomass. But we'll hone in on the wetlands for our talk today. I mentioned a little history. I want to highlight the FluxNet methane exercise that we started about 5 years ago. We gathered data from about 80 sites. We didn't set up these 80 sites. These were investigators like yourselves who were already taking measurements. So we aggregated these data, gap filled, standardized them, and made them available to the community overall. And you see the distribution of that map in the bottom left. You'll see a couple things there. The two strongest potential tipping points for methane are the two places in the world where we have the poorest representation of towers currently, and that's true for just about whatever you measure today. That's in the Arctic and Boreal, where our representation's not terrible, but not great, especially when you look at countries like Russia. But then you look at the tropics, which is my emphasis for this morning, and we have almost literally a couple of sites, flux tower sites across the tropics. And so we're trying to remedy that through a new grant that we're coordinating through Stanford and McGill, and setting up a version 2 of this FluxNet call that we hope to pull in other sites. Then I'll talk about why the tropics, why I care about the tropics in a minute. So with this first V1 database, I forgot to, I had a shout out here to all the Berkeley folks. We are in Berkeley. A shout out to all the Berkeley folks who've contributed to this work. So thank you all once again. So with this first V1 database for FluxNet methane, we were able to look at factors like the effective temperature on emissions, and it wouldn't surprise any of you perhaps that higher temperatures, all else being equal, increase methane emissions across, these are primarily wetlands around the world. Now this isn't the same as warming a site. Each of these dots is a different location, so sort of a space for time approach, but you see a very strong and pretty linear relationship for temperature, either air temperature or surface soil temperature with emissions as a function of temperature. So all else being equal, we expect methane emissions to go up as the Earth warms, but the all else being equal part is the tricky part, and that's the rainfall and hydrology. We have to have waterlogged or low oxygen conditions for microbes to generate methane, and that's much harder to predict, both locally and globally, than an increase in temperature is. So when we think about our flux tower sites and building predictors for these sites, we really need to think about how we assess waterlogging, redox state, and the saturation of sediments and soils. Another shout out to all the postdocs on the left from my group who contributed to this. Some of them are here today. I've seen, I see Avni in back. Kyle's here at Lawrence Berkeley now. Sarah Knox can't be here. She's a faculty member now in McGill. I don't think Gavin's here. You here, Gavin? Gavin led our upscaling effort. So anyway, thank you to all of these folks, as always. Okay, so now let's think about tipping points. That is the sort of the agenda for today. And the two obvious ones begin with the Arctic and boreal systems. And this is an article from the Popular Science, and I like the title, "The Arctic Might Be a Methane Time Bomb or Not," which about covers it. But the problem with the Arctic is that we know that there's a lot of carbon up there, but we don't know the balance of emissions of that carbon as carbon dioxide or methane, which once again depends upon the wetness and the local hydrology. And a point the Shakova et al. Work in the East Siberian Sea, that probably the strongest data sets to suggest that methane emissions might already be increasing in the Arctic, though we don't think that's happening globally yet. But if and when it does happen, it's bad news whether the carbon goes as carbon dioxide or as methane, because this is work from Gustav Hugelius, there's more than 400 billion tons of peat carbon there, and almost half of that is permafrost protected. So we know when that system starts or continues or accelerates to thaw, some of that carbon will also thaw and become available to microbes and go to the atmosphere as CO2 very bad, go to the atmosphere as methane potentially catastrophic. So that's why we care about the peatlands and northern systems. But we also have to think about where methane comes globally. And this is a latitudinal map. I'd like you to focus on the right for this image for a minute. And you see at the top, the small pie is the amount of methane that's emitted from northern latitudes. The middle is temperate, and the large pie in the middle is the tropics. So you see that tropical emissions, even under steady state, no, I'm sorry, Arctic emissions, even under steady state, are quite small relative to the global balance. So they're hard for us to assess against a small background, but they could go up quite a bit, and with our poor observation network, make that hard to assess today, but still be relatively small to the emissions from sites in the tropics. For instance, the large green wedge, that's tropical wetlands, and the blue wedge, that's agriculture in the tropics. So I'm going to focus for the rest of today just thinking about how do we assess tropical emissions and how can we expand the FluxNet system there. And many investigators are already worried about whether tropical methane emissions are already increasing. And these are just a few papers. The Lint paper from a few years ago. Yu and Nisbet has been banging this drum for some time. And then the Shushi Peng paper from a couple years ago in Nature. There is a lot of, in my opinion, a lot of somewhat circumstantial evidence for increased tropical methane emissions, but the on-the-ground measurement basis for these assessments is actually quite weak. And it's partly because of a lack of observations, and not just flux towers, but chambers and other systems too. So we really need to think about how we know what we know and how we can bolster the confidence for what's happening in the tropics. An example of a satellite-based approach, this is Zhuiying Yu's work, who just left our lab. This is a tropomi analysis for change in methane emissions from 2019 to 2023. And the boxes are where tropomi suggests methane emissions have changed. So you see a hotspot around Beijing in China. And all the other hotspots are primarily tropical, particularly that strong one in the Congo. But the tropical ones are also the hardest to assess with confidence using satellites. They're cloudy, they're hard to see with satellites. So it really does, for me, point out the need to balance or sort of supplement these satellite-based approaches with a network of flux towers. And that's what we're trying to set up with your help. So thanks to Zhuiying for this work. So when we set up the FluxNet V1, we incorporated all the sites in blue that are on this figure. And we got done with that project, and surprise, surprise, the weakest data that we had was for the tropics. So in our new MORE grant that's ongoing now, we're trying to work with local investigators, shout out to everyone along the bottom, in Peru, Brazil, French Guiana, and in the Okavango, to either set up new towers in the locations in red, reestablish towers that ran in the past but had run out of funding, or add methane instruments to existing flux towers now, which is one of the cheapest ways we can go to increase our methane assessment. So you see that belt along the tropics. That's what we're after with this new MORE grant. And we have a couple postdocs on the project here, Fa Li and I think Rafa Stern, and Fa will be giving a poster later on this project. We've already begun working on FluxNet Methane V2, so we put out an open call for data. And in addition to the 80 sites that we started with, we've gathered about 80 more sites where people have said they'll contribute site year data. There's a lot more representation across the tropics, in Africa, for instance, Southeast Asia. Still have a lot of work to do, but I guess this is really the reason I'm here today speaking to you, is to try and engage with you and people you know around the world to bolster this observation network. So here's our call. Please join the effort. Just as a brief mention, our FluxNet V1, the investigators who contributed data, we had more than a dozen papers of synthesis aspects that we put together, and the people were partners in. So there was a lot of payback for the intellectual payback for the effort. We hope the same will be true for V2. Last sort of informational slide, in addition to setting up this network, we have a workshop we're hosting either at Stanford or here at Berkeley, October 21 to 23, as you see, and that's to help people gap fill and process their data, bring it online for FluxNet Methane. If you have any interest in participating in that workshop, you can call me or talk to Fa Li, who will be at his poster tomorrow. And there's Fa's email. And then finally, we have a postdoc opening for field work in the tropics that if anyone's interested, please let me know. Trevor mentioned my book. I'll end with a a shameless plug. It's a new book on climate solutions, a trade book, with a focus on methane, again, as a lever for the greenhouse gas that we have the most control of over the next decade or two to reduce temperatures. So that's all from me. And again, just a call for engagement, and thanks to AmeriFlux for everything you do.
Thanks, Rob. Super interesting and great to see the efforts behind the new FluxNet methane database. We have time for one question as our next speaker gets set up. Does anybody in the room or online have a question? If you could use the microphone just for the benefit of those online.
Are there any efforts on trying to estimate the leakage from using natural gas?
There are many, many efforts, not so many efforts using flux towers, but everything from ground-based observations to the new satellites that launched. Carbon Mapper just launched a couple weeks ago, MethaneSat. So there's a much larger community, in my opinion, looking at the oil and gas leakage of methane than there is trying to understand emissions from natural systems like wetlands and fresh water. Does that answer your question? I'm not sure what aspect you were. Okay.
Just the train, the string S shape is very similar to, when the use of natural gas, has been increasing.
Okay. All right. Thank you all very much.
Thank you, Rob. Thank you once again. There's a question online. Not getting off so easy.
Yeah, I had a question, and that was regarding the last presentation, regarding the topic of wetland, or the topic of peatland re-wetting. If you're looking at the data and especially the warming and the tundra, but the significant amount of methane coming out of wetlands and tropical areas, what is your perspective on the approaches of peatland re-wetting, which is being suggested in the European environment as well as in the American environment? To what extent are we trading other ecological benefits for significant increase in emissions from decomposition into methane?
Great question. Long answer, maybe long question. I would look at people like Allison Hoyt, who's here in the room. Allison can raise her hand, who's an expert on tropical peat. The aspects of peatland restoration are complicated. Just as in the Bay here, you have a balance of carbon dioxide uptake and methane emissions when you re-wet. Long term, of course, the balance for carbon uptake overtakes the losses of methane. But in the next, according to Dennis's work here, 25, 50 years, it takes a long time for the carbon storage to offset the methane. So it's complicated. But I actually have a chapter in my book on this. It's not just about greenhouse gases. It's about diversity and other goods that wetlands and peatlands provide. So we have to think about those too. So I still believe in peatland and wetland re-wetting, even if it costs us a bit of methane in the short term. Thanks for the question.
Thank you, Rob. Thank you once again. Okay, I'd like to welcome our next speaker, who's Jackie Matthes, who's going to be talking to us about long-term observations of carbon and water cycling in response to precipitation extremes. Thank you, Jackie.
All right, from the globe to a small patch of forest in Massachusetts. So I'm Jackie Matthes. I'm a senior scientist at Harvard Forests, and it's wonderful to be here with you all today to share some insights into our long-term work at Harvard Forests and understanding the carbon and water cycles. Quick shout out, you can see Bill's poster for a lot more details about changes at Harvard Forests through the past 3 decades. And also thank you to my co-authors on this, Sam, Naomi, and Amara, who are all part of my lab group. So Harvard Forest is a seasonal, temperate, deciduous forest. You can see it here in its glory through all the seasons. And Harvard Forest has a long-term flux tower, USHA-1, in their AmeriFlux network that I'm sure many of you are familiar with, where our data records extend back to 1991. And so work at this site really helped to lay some of the early groundwork in appreciating the strong carbon dioxide sink in temperate forest ecosystems. You can see here this sort of seminal figure showing the changes across the seasons in the strength of the carbon dioxide uptake, which was much larger than previously appreciated in its time. And so today I'm going to really talk about how we're leveraging this long-term data record at Harvard Forest to understand shifts in decadal water cycling, and then how that might be translating into changes in the carbon cycle. And so the two main climate change effects we're seeing within New England with respect to the water cycle are, first of all, an increase in precipitation and large storms, and secondly, a loss of our wonderful wintry conditions in New England. And so first we'll talk about precipitation. You can see precipitation, total annual precipitation is here in the light blue bars, where the height of the bars represent the total amount of precipitation in that year. And if we look, this is going to be a common theme throughout this presentation. Before 2010, things were kind of like steady. There was a little bit of variation, but not too much. After 2010, things get really crazy. We had a lot more variation in our total incoming rainfall during this time period. Interestingly, we can see across our record, there was really no significant trend or change in evapotranspiration in response to this change in precipitation. And just one more thing to highlight from this graph, we can see in the dark blue, this represents years with the water surplus, and the dark red represents years with the water deficit. And so since 2010, we've experienced more variation, our rainiest years and our driest years as well during that time period. And so in addition to this sort of change in total rain, like I said, more rain is falling in heavy storms, and heavy storms represent a larger fraction of our total overall rainfall. And so I saw these patterns and I thought, okay, I'm going to go look into soil moisture to see how much soil moisture has changed in response to these questions or these drivers. I previously was really interested. I worked on methane a lot. I was like, this is really important to look at how moisture is increasing and it's decreasing. This was one of those moments where I thought I made a mistake when I was looking at our soil moisture data. I'll talk about in a second why that was not definitely not a mistake. But despite this higher overall rainfall, we see a long-term decline in soil moisture. And again, this is despite there being no trend in evapotranspiration. So it's not more evapotranspiration causing drier soils. It's because our soils are really rocky. So we have these horribly rocky post-glacial soils at Harvard Forest that drain really, really fast. There's a low water holding capacity. And so these really large storms do little to sustain soil moisture within the soil column. They just flush right through the soils and sort of move out as sort of deep runoff from the system. And so the other big shift we saw around 2010 at the same time was a change in our carbon dioxide cycle, or our carbon uptake and ecosystem respiration at the site, where we can see prior to 2010, we were sort of getting increasing carbon uptake year after year, same with respiration. And then after 2010, we've had declining rates of carbon uptake and respiration as well. I should say the forest is still a sink for carbon, but we really see a turnaround point in that trend. Apologies that I showed GPP as positive here, but I wanted us to be able to compare the lines more easily. So it's the opposite sign. And so digging in a little bit to figure out why is this carbon uptake declining, we really see a turnaround point if we look at the rates of carbon uptake during like the happy light conditions for the canopy. So during mid and high PAR conditions, we see 2010 is really an inflection point in the mean carbon dioxide uptake during those sort of ideal PAR conditions for plants to be photosynthesizing. And so what's happening during these sort of happy par conditions that might be causing this turnaround? So first of all, during the growing season, we're seeing increasing temperatures. This might be driving more sort of demand from the atmospheric side. Many people have seen this in their work, and we're also seeing rising VPD, particularly during these sort of mid-par conditions, a really strong increase in the vapor pressure deficit during these times when light is ideal for photosynthesis. And so now if we sort of break apart and think a little bit about the growing season in contrast to the non-growing season, again, in the growing season, we really don't see a strong trend in either potential evapotranspiration nor actual evapotranspiration over our data record. However, in the non-growing season, we see this really large increase in the amount of evapotranspiration that's happening outside of the growing season. And this is because of our warming winters. And so we see both an increase in the actual ET and in the, you can see in the pink dots here, this is the potential evapotranspiration over this time period. And so this increased evapotranspiration during the winter sets the stage for drier springs. And so drier springs then set the stage for drier summers. And we found in looking into our data that dry spring conditions are 80% more likely to lead into summer water deficits. And so these changes during the non-growing season are sort of spilling over to affect the growing season. And we can see this if we look at the relationship between wintertime evapotranspiration and annual GPP in sort of the following growing season. This is looking at the first half of our data record up until 2009, and we can see this strong relationship where the more water that evaporates during the winter, the lower the GPP in the following summer. And then if we look since 2010, we can see we sort of explode into this new area of the graph with higher and higher rates of wintertime evapotranspiration and lower rates of carbon uptake. There's much more variation, though, I should say here too, in these later years. And so just to summarize, we're seeing changes at Harvard Forest from the supply side as these more intense rain events flow quickly through our soils, causing declining soil moisture. And we have higher evapotranspiration during the non-growing season that's sort of setting the stage for drier conditions in the spring and then in the summer. And then we're also seeing some evidence for changes in sort of the demand side of water, where the weather conditions during what would otherwise be ideal par values for photosynthesis are warmer and drier, potentially feeding back to cause some canopy stress. So with that, I want to give my sincere gratitude to the AmeriFlux Management Project who have helped to support this work, in addition to the National Science Foundation LTR program. And I just wanted to, I'll leave this up here. We have a great program at Harvard Forest that, to be honest, is underused, called the Bullard Fellowships. These are paid short-term or long-term opportunities to collaborate with me and other folks at Harvard Forest. I would be really glad if people wanted to do flux work or remote sensing. We have an amazing canopy lift. You could do leaf level measurements and things like that. So you can check it out, and I'm happy to talk about that more as well. With that, hopefully I have time for a question.
We have time for a few questions. Any questions in the room or online?
Have the warming winters changed the timing of leaf out?
Yeah, that's a really great question. So in our data, we saw sort of earlier and earlier leaf out through about 2010, 2012. But since then, the patterns have also become more variable in leaf out as well, that have kind of obscured some of that earlier trend that we saw. So I would say our earlier data show a pattern, but more recently it's become a little bit harder to see that same signal. Yeah, go ahead. Oh,
Repeat the question.
I'll repeat the question, sorry. Right, so how much of the winter loss would be sublimation? I would say, this is sad, but I would say very, very little, because we've had extremely little snow last winter. We just, had like hardly a sprinkle for some of the year. It was the ground didn't freeze last winter at Harvard Forest. It was yeah, a sad year for snow. Sad year for all of the ski mountains. Yeah.
Maybe a quick check to see if we have any questions online. Russ, do you want to unmic and go ahead?
Yeah, Russ,
Yeah,
you can go ahead. Oh, yeah.
Can you hear me?
Yep.
I was just wondering, with more deep drainage, have you noticed any differences in the water table? And how deep is the water table, and do the trees access water from that depth?
Yes, that's a great question. So we are starting to delve to our deeper parts of hydrology at Harvard Forest. We don't have a good measure of the water table in uplands, but we do have gauges in streams that are sort of draining various parts of Harvard Forest. And so we do see increases in runoff that are associated particularly with very wet years, which we think helps to support some of this sort of guessing about the water draining really quickly and then moving out of the system. Yep. Thanks. Okay, we got to wrap it up, but talk to me later about this. Anybody who's online, send me an email. I'd be glad to chat more about this. Thanks.
Thank you, Jackie. Lots of questions, I'm sure, about long-term dynamics in general, but particularly at Harvard Forest. So I'd like to welcome up Chris Still and Linnia Hawkins, who's joining online. This is a team talk focused on the heat dome event in 2021 and its effect on the Pacific Northwest. Chris, over to you and Linnia.
I think everyone can see that. Well, thanks for the invitation. Thanks for the organizers. I know how much work this is. I appreciate the opportunity. And I'd like to do, a joint talk between myself and Linnia Hawkins at Columbia and NCAR, who used to be a postdoc with me and worked partly on this project, and then Chad Hansen here in the room is a contributor. The title is really kind of a big title. This is a larger analysis that we're working on, and I want to really just focus on the flux aspects of it, but be assured we're trying to look at many aspects of impacts of the heat dome event on trees and forests of the Pacific Northwest. And there's a lot of contributors here, and lots of agencies have played a key role here. And let me try to get a laser pointer. Yeah, and a key role in looking at this event. And just in case you are not aware of this or you've not heard about it, here's an example of it. It was a massive climate anomaly, one of the most extreme on record. This is the NASA land surface temperature anomaly. For roughly the week bracketing the event, you can see the magnitude, the spatial magnitude of the event was tremendous, and the intensity, what was most notable about this event. I liken this to kind of like a gigantic bruise on the North American continent. And depending where you're at, it started sort of the 24th, 25th of June, and then extended in some places later into July, but in the areas where we're looking at in the Northwest of Oregon and Washington, it was just a short event, like 4 to 5 day event, but remarkably intense. And it was record shattering. All sorts of records were broken all over the place in Oregon, Washington, California. There have been a number of papers written about this. It was such an incredible event. It was sort of one of these massive global change type heat events. This is just one example of over 60 papers written on this event in the climatic and biologic and fire and human health literature. This paper was one of the early ones, characterized it in standard deviations from the normal as the 6th most extreme heat event since 1960. So really an incredible event that was a shock to the system, and it gave us a chance to actually examine what this massive heat shock would do to forests and ecosystems of the Pacific Northwest. Just to give you a spatial map, this is an example based on PRISM data. This is standard deviations from the long-term mean for one of the hottest days of the event, June 27th, 2021. These are the areas largely west of the Cascade Mountains in Washington and Oregon. And you see some remarkable hotspots up here on the Macaw Peninsula of the Olympic Peninsula, 7 standard deviations. Lots of coastal regions reach 6 to 7. But again, many areas in the Willamette Valley and the western slopes of the Cascades reach 4 to 6 standard deviations from the normal T max for that day. So just to give you a sense of just the remarkable nature of this event. That was air temperature. We know also from thermal imaging in upper forest canopies of old growth, 60, 70 meter tall ecosystems at the Andrews Forest, that the leaf and canopy temperatures exceeded air temperatures by 5 to 12 degrees Celsius. So the leaves themselves, not surprising in the sun, were quite a bit hotter than the air. And we think for many hours during this event, as you can see here by the solid line, they exceeded what are typical damaging threshold temperatures for leaves for many hours at a time. And so it begs the question that is the focus of this analysis and what I want to talk about today. What did it do to trees and forests of the Pacific Northwest? So this is not just your garden variety heat wave. This was a real humdinger of a heat wave. And we're looking at this at multiple different scales. I'm not going to focus on these, but we've been examining all sorts of things from on the left, massive impacts on the demography. There was just lots of seedlings of all species were wiped out. There's definitely a species sensitivity to this. Certain species are much more heat sensitive than others. Impacts on canopy. There was massive scorching on the order of 90,000 hectares of forests in the Pacific Northwest actually experienced canopy dieback and canopy, almost like a coral bleaching event, but for forest ecosystems. Impacts on growth and things like that. But what I want to really talk about today with Linnia is, since this is AmeriFlux, is the EdiFlux component. We've been analyzing data from 4 different AmeriFlux sites in Oregon, Washington, and British Columbia, looking at carbon and water fluxes. We've also been looking at phenology and satellite data and things like that, but really the focus is just on the fluxes. And so with that, I want to now pass this over to Linnia, who's online, to talk about some of the ecosystem flux impacts.
Great, thanks, Chris. So as Chris mentioned, we looked at 4 sites from north to south, the Canadian site on Vancouver Island, 2 neon sites in western Washington, Wind River and Abbey, and then the Metolius Young Pine site in Central Oregon. And these are all evergreen needleleaf sites, primarily dominated by Douglas fir, except for the Metolius site, which is ponderosa pine. And so these time series show daily mean net ecosystem exchange, with 2021 shown in the black line, and then the range across all other years of flux data shaded in gray. And then the heat dome event is the orange band. And we see that all 4 sites had positive NEE during the heat wave, meaning that these forests were all a net source of carbon to the atmosphere during this event. And we have found that this is primarily driven by a decrease in gross prime productivity rather than an increase in respiration. Some of these sites were only briefly positive. Wind River in the second panel had positive NEE in the days leading up to and following the event. But the ponderosa pine site, the Metolius site in the bottom panel, once NEE became positive during the heat wave event, it remained a net source of carbon to the atmosphere for the remainder of the growing season. And so next slide, another way to visualize these effects is to look at the cumulative annual NEE. And again, 2021 is shown in the black and all other years are shown in gray. And I like this visual because it highlights how the heat dome altered the trajectory of NEE for the remainder of the year for all 4 of these sites, particularly at Wind River, where in the second panel, where it took several weeks before NEE started trending back negative. And then in the bottom panel at the Metolius site, 2021 was a net source of carbon to the atmosphere, which is just highly unusual for this site. And particularly because this year had about average soil moisture conditions as well. So it just emphasizes the role that this heat wave played in the annual carbon uptake at these sites. Next slide, please. So now transitioning to latent heat fluxes at the 2 neon sites, again, showing a daily mean in black for 2021 and all other sites or other years shaded in gray. Both of these sites lost a lot of water during the heat dome event, and then evapotranspiration rates were fairly low compared to other years for the remainder of the growing season. And the Abbey site in the top panel had this really remarkably high latent heat flux during the heat wave. And interestingly, I think this was partly due to high nighttime evapotranspiration rates. Next slide. So zooming in on just the 10-day window around the heat wave event, I'm now showing 30-minute latent heat fluxes in blue and sensible heat in black. And there's really high latent heat fluxes during this event, but particularly in one night on day 178, 179, the air temperatures never dropped below 30 degrees Celsius. And this night was also particularly hot and dry and windy, and that translated to these really high nighttime evapotranspiration rates during this event. Next slide.
Okay, thanks, Linnia. And just to wrap up, yeah, extraordinarily high nighttime water losses that were corroborated by other measurements as well. We know from things like the infrared thermometers at the neon sites that the canopy cooled remarkably. So a massive loss of water. And there are interesting images from the phenocams that sort of show how sort of droopy looking the canopy became as it became dehydrated. I do want to just show here an example of where we can confront models with data, where we have these amazing eddy flux data that are really high quality, and we can compare them to process models. This is an example of the CLM community land model out of NCAR, which has been parameterized for that site using site level driving data. And one thing you see is the neon latent heat is in blue, right around the heat dome again on that orange band, and the CLM model is in red, and you can see that it just completely misses the event here. You can see the one-to-one line here, and in the red polygon, I've shown those nights for which there's a complete, the measured eddy flux latent heat is way, way higher than what the model actually predicts. So this is an example of where we can actually work to try to improve the model for these extreme events, which are only going to increase in magnitude and frequency. And just to wrap it up, the response to this heat event was really individualistic. There's a huge amount of tree level information we have from things like dendrometers and other things that are really fascinating. There's a very species specific component as well, and somewhat site specific. The younger stand, that Abbey site, tended to recover better than some of the other stands. The responses varied a lot, as I mentioned. Visual foliage scorch, kind of like a mass bleaching event. Non-obvious leaf damage. Sites that did not experience canopy bleach or scorch actually still had substantial impacts on their tree growth that has lagged and continued into the present day. The heat event actually has impacted tree growth now into the present day. The timing of the heat event is really critical. This has been pointed out before, but an early to mid-season heat event is way more damaging to a forest than a late season one. And finally, process models are really, at least in this example, they probably are not capturing these sorts of ecosystem responses to these extreme events. Thank you.
One quick question.
Yeah, hi. My question is about the temperature profile in the canopy. So some of the canopies are very deep, high LAI, like Wind River. How much did the temperature actually increase through the canopy as well?
Yeah, I mean, what you generally saw was there was an increase throughout the canopy as well. And some people actually in the audience here, there's a couple of grad students who've worked on this, but there are differences in the top of the canopy versus down through the canopy as well. But there was a massive, like at the Abbey site, for example, we have temperature data from the infrared thermometers down through the canopy, and there was certainly a cooling relative to the air at the adjacent elevation. So they were certainly cooling, but they were still remarkably hot. I haven't looked in too much detail what the actual gradient would be within and through the canopy, but Keenan, who's here, has looked at this in a lot of great detail and has a cool poster on this topic, actually. So absolutely would, and especially at a place like Wind River versus Abbey. Yeah. Thank you.
Thank you, Chris, and thank you to all our speakers this morning. I would clap if I could. Thank you. Okay, so this concludes our morning session. What we're going to do now is we're going to go and do a group photo, stretch our legs, and enter into a period of more interactive engagement of today's meeting. So we're going to do the group photo that is outside on the lawn behind the patio. And then after the group photo, we're going to start the poster session. And so the posters you can find here. Poster session goes into lunch, after which we have the poster session again continuation. So we're really hoping to have enough space for social interaction, for discussion, collaboration, and obviously to engage with the poster presenters. Okay, thank you. I'll see you outside for the photo.